In this chapter, we're going to be reviewing and introducing concepts in geometry and transformations. In this lesson, we want to take a look at the various types of quadrilaterals that exist and their properties.
Okay, hi everybody. So in this lesson, we're going to take a look at quadrilaterals. Okay, so a quadrilateral is a four-sided planar closed object. Okay, now, basically, planar means it's on a flat sheet of paper, and closed means that it's the sides are like connected to each other. So, for example, this right here, this is a four-sided open object, right? Because the ends don't close; they're not connected. With a closed object, there's a definite inside and an outside. So, I mean, that aside here, you probably really weren't all that concerned about that. Now, the sum of the angles inside there is going to be 360 degrees. For a triangle, it's 180 degrees, but for a quadrilateral, it's going to be 360. And there are lots of different ways that we can classify quadrilaterals, and that's what we're looking at here. So, to start off with, here we go. Once you've identified that you've got four sides, then there's three different directions you can go here. If you come over here, if the opposite sides are parallel to each other, okay, then we call it a parallelogram. Now, there are some neat properties about this. Okay, these two sides are going to be the same length. These two sides are going to be the same length. Okay, the diagonals will bisect each other. If you cross there, the diagonals here will cut themselves in half. Now, they're not the same. The diagonals are not the same length. This diagonal will be shorter than this one, and I think that makes sense because of the way it's been leaned over there. Okay, but they'll cut each other in half. Additionally, we know that these two angles here, because of the parallel lines here, these two angles will add up to 180. Yeah, but so will these two angles add up to 180. So some properties of the parallelogram. Now, after that, this breaks up into two other sorts of parallelograms. This down here is the familiar ones here. We've got the rectangle and the square. Okay, and I mean you're familiar with the rectangle and the square here. Okay, with the square, all sides are the same. With the rectangle, two opposite sides are the same, but you've got the right angles at all the corners. Or you go over here and you talk about a rhombus, and in a rhombus, a rhombus is like a parallelogram. Okay, it's been kind of pushed over. Opposite sides are parallel, but in this case, the opposite sides are the same length. One other interesting thing about the rhombus here is that the diagonals, if I draw the diagonals in, not only do the diagonals bisect each other, okay, which means they cut each other in half there, but they're perpendicular to each other, which is kind of an interesting property of the rhombus. Now, if we go up here to the kite, come down the middle here, the kite is a shape where you've got two sides are the same length and then two other sides that are the same length here. And what happens in this situation right here is when you draw the diagonals in, the diagonals also form a 90-degree angle with each other, this one here gets bisected, but this one doesn't. This one here, this part right here is going to be much smaller than this one. Okay. Anyway, so that's the big one here, is that they intersect at 90 degrees. Now over here, if only one pair of sides are parallel to each other, and the other sides aren't, we call that a trapezoid. Okay. From there, once you've identified that, well, only two of the sides are parallel to each other, well, then you've got a couple of options here. You could have specifically a right trapezoid, okay, in which case the only difference here is that these two angles here are 90 degrees to each other, and you have to have a pair of them. They'd have to be together like that. Okay. Or you have, oh, and you can't see it, it's gone off here. You have what we call an isosceles trapezoid. Unfortunately, it's printed into here, where this side and this side are the same length. Okay. Now, if the two far sides here are the same length, then what happens here is your base angles are the same as each other. So like these two angles would be identical, and then up here these two angles would be identical to each other as well. Okay. But of course, clearly you can't see that. Anyway, let's take a look at some questions now that deal with the information that you're getting in this chart here. It's going to be handy for you later on to kind of keep this chart sort of handy as we go through. Okay, so let's take a look at some questions here. So first of all, find the measures of the missing angles here. Okay, and what kind of quadrilateral is this? Well, because I can see that this side is parallel to this side, and it's just one pair of parallel sides here, I know that this is going to be a trapezoid. Okay, that's easy. Now, take a look a little harder at it and notice that this side right here and this side are the same length. Well, that means that this is an isosceles trapezoid, which means it's got some interesting properties to it. First of all, I know that these two angles up here are going to be the same length. So I know that this angle here is going to be 118. Now, additionally, because these two lines are parallel, if I was just to extend that line, and then extend this line, now I have got two parallel lines with a transversal, and I know that these two lines in here, these two angles here should add up to 180, okay? Which means this angle here has got to be 62 degrees. In order for these two angles to add up to 180, this has got to be 62. And once you've established that, because it's an isosceles trapezoid, I know that this angle over here must also be 62 degrees. And so there we go. That's how you can use your knowledge of what kind of quadrilateral this is to find the missing pieces of the shape. Okay, so in this question we read that Stephanie is making a planter in the shape of a trapezoidal prism. Okay, which basically means it's got a trapezoid at the base, and then we just build up from there. I mean, it looks like an animal trough sort of thing, if you want to think of it like that. So anyway, so let's go down here and take a look at the questions here. What is the measure of angle ABC? Now, this is not, sometimes people misinterpret this. This is not angles A, angle B, and angle C. This is angle ABC. Starting at A, go to B, go to C. It's this angle right here. Now, based on the information that we've got here, I got to assume that this line here goes straight up perpendicular from base to base, so that this is the height of the trapezoid. Now, if that's the case, I can do the same thing over here to do that. Now, this is 35 centimeters, which means going straight up here, this distance right here is going to be 35 centimeters. Now, that leaves me with 5 centimeters left over across the top. So that means this has got to be 2.5 centimeters, and this right here has got to be 2.5 centimeters. Now, I hope that makes sense. Okay, so 35 centimeters, I go straight up. What I'm left with on either end here is going to go to those triangles, right triangles here. Well, I've got a total of 5 centimeters total to go to these two triangles, so 2.5 here to 2.5 here. That is now enough to help me figure out what that angle is. So if I'm looking for this angle right here, what I've been given is the opposite side and the adjacent side. Well, that's tangent. So the tangent of angle ABC is going to equal the opposite side, 30, over the adjacent side, 2.5. Now, in order for me to get the angle, I actually have to use the inverse trig function. So it's going to be ABC, angle ABC will be equal the inverse tangent of 30 over 2.5. Okay, and now I'm just going to go to my calculator to figure that out. And it's going to be the inverse tangent of 30 divided by 2.5. And to the nearest degree, I get 85 degrees. Okay, so 85 degrees right in there. Good. Now, how much soil in centimeters cubed can the planter hold? Okay, well, volume is always equal to the area of the base times the height, or the length, if you want to think of it like this. It's the area of the base times the length, depending on how this works here. And in this case, it's going to be the area of the base times the length. So what I need is the area of this trapezoid, and then I'm going to multiply it through by the length of this planter. Now, as soon as I did this, I see a problem. These are centimeters. That's a meter. So one of the things I need to do here is convert these all to the same units. And let's convert them to centimeters here. So 1.5 meters, if I move that decimal 2 places to the right, okay, will be 150 centimeters. And now I'm good to go. Now the area of a trapezoid, okay, so the area of a trapezoid is going to be 1/2 the height, okay, times the sum of the two bases, base 1 plus base 2. Now, what I mean by that is if you've got a trapezoid here, here's your base 1, here's your base 2, and then your height is the distance between them. So it's the sum of these two, the top and the bottom, divided by 2 multiplied by the height. So my volume in this particular case here is going to be, first of all, the area of the base. So I got to figure out the area of that base here. Well, that is going to be 1/2. The height is 30. And then it's going to be the sum of these two right here. So that will be 40 plus 35. That right there, okay, that right there is the area of the base. Now what I got to do is multiply that by the length of the whole thing, so 150 centimeters. There it is. This is the base area of the base times the height, or times the length here. So now this is just calculator work, and so that will become 1 divided by 2 multiplied by 30 multiplied by, well, it's the sum of those two, so I got to make sure I put those in brackets there, and then multiply that by 150. Whew. And I get 168,750. Now I'm in centimeters, centimeters cubed. Now that seems like a really big number, but centimeters are small, okay? And that's at 1.5 meters long. That's relatively large, okay? So yeah, I'm not surprised that the number of centimeters cubed that I'm getting here is that big. So that's not a concern for me. That makes sense. Okay, in this question we read that Fred is sewing a kite using white and gray fabric. Okay, so here it is. And then here are the dimensions that we're given here. So the question is, to start off with, what are the measures of angle BCE? Okay, so BCE is going to be this angle right there, and CBE, okay, which is going to be this angle up there. Okay, so what kind of triangle is BEC? Okay, well, let's figure that out here. So first of all, I know that the distance across the bottom here is 80, but because I know that this is a kite, okay, because I know this is a kite, I know that this line that comes straight down the center cuts that line in half. So I know that these two sides are going to be the same here, and if the total is 80, these are both going to be 40 centimeters. Now, additionally, I'm told that this side right here, BE, is 40 centimeters. So to get angle BCE, which is the first one I want, I'm going to look at this angle, and I know the opposite side. I know that this is 40. And I know the adjacent side, it's also 40. So that's tangent, right? If I know the opposite and the adjacent. So I know that the tangent of angle BCE is going to equal 40 over 40. So triangle, wow. Angle BCE is going to equal the inverse tangent of 40 over 40. Okay, and after I go to my calculator, you'll discover that right away that this is 45 degrees. Now, I can do the same thing with the other angle here, this CBE. It's just that this time the opposite and adjacent switch, but they're the same size here. So the tangent, once again, of angle CBE is going to equal 40 over 40. And because that's basically the same work, I can already tell you that angle CBE is going to equal 45 degrees. So what I've got here is enough information to tell you that what kind of triangle is this? Well, this is a right triangle. First of all, because I know that there's going to be up here, I know that this angle BEC is going to be 90 degrees because I know that the diagonals, okay, I know that the diagonals in a kite meet at 90 degrees, but it's also going to be an isosceles triangle. And there's a couple reasons for that, but most importantly because these two sides are the same. So it's an isosceles right triangle. Now, what are the measures of angle EAD and ECD? Okay, EAD, I'm going to use the black marker here. EAD is going to be this angle right here, EAD. And then ECD is going to be this angle right here. So EAD, ECD, those two angles here. Now, I can actually shortcut this a little bit here because there's some symmetry in this problem. I already know, for example, that this is 70 centimeters right here because of this. So let's focus on EAD. If this is my angle here, 70 is opposite and 40 is adjacent. Now, when I flip over and look at this side, for this angle here, 70 is opposite, 40 is adjacent. Like, it's the same thing. It's the same thing. And it's still tangent. So I'm just going to focus on angle EAD to start off with. So the tangent of angle EAD is going to be the opposite side, which is 70, over the adjacent, which is 40. And so angle EAD will equal the inverse tangent of 70 over 40. Okay, so I'll go to my calculator. Inverse tangent of 70 divided by 40. Oops, a little bit of a glare there. And I get 60 degrees. Okay, I get 60. We'll round that to the nearest degree there, 60 degrees. And then because I know that ECD is built using the same ratios here, I also know that angle ECD is also going to equal 60 degrees. Now, what are the measures of angles BCD and BAD? Okay, well, what angles are those? Well, BCD is this big angle right here. BAD is this big angle right here. Now, because of the symmetry in the problem, I know that they're going to be the same. Okay, I know that BCD is going to equal angle BAD. And what it's going to equal is the sum of these two. Well, I know that this is 45. And I know that this angle right here at this ECD was 60 degrees. I just figured that out. So that means altogether, when I add those together, I'm going to get 105 degrees. Now, the last question here about this is how much of each color was used in centimeters squared? Well, what I'm asking you to do here is to come up with the area of the white and the gray. Now, they're going to be the same, okay? So the area of the white will equal the area of the gray. So we just got to pick one. So let's pick the white one here. So I've got two triangles, okay? One where the base and the height are both 40 centimeters. So my area is going to be 1/2 the base times the height, which is going to be, in that case, 40 multiplied by 40. But I'm going to add to that the base and height of my other triangle here, whoops, this one, where the base is 40 and the height is 70. So 1/2 40 times 70. Now, this is just calculator work. So I go to my calculator. Oops, make sure you can see that. So it's going to be 1/2 multiplied by 40 multiplied by 40 plus 1/2 multiplied by 70, or 40 in this case, what I did, multiplied by 70. Here I get 2,200 centimeters squared of fabric. And that's going to be the amount of fabric that we've got for both the white and the gray. Because there's symmetry in the problem, the shapes are the same. Okay, now I also wanted to take a look at this problem right here. It says solve for the indicated length or angle and identify the type of quadrilateral. Okay, so let's just take a look at the handful of problems we've got here. The first one here, I'm looking for angle A. That one right there. Now, notice it's a quadrilateral. It's been slightly tilted over here, so this is a parallelogram for sure. Okay, parallelogram. But I can do even better than that because all four sides are the same length. I see that because of those little marks there. So I know that this is actually a rhombus. That's the shape that I'm looking for. Now, in a rhombus, like any parallelogram, two adjacent angles here, right next to each other, are going to add up to 180 degrees. So for me to get what angle A is simply going to be 180 minus 65 degrees. Okay, and when I do that, I get, 65 degrees is going to be 115 degrees. Okay, that's the value for A. Let's take a look down here. Look at this shape. Now again, it's a quadrilateral, and notice this side right here is parallel to this one, but these two sides aren't. So this is a trapezoid. Okay, right off the bat. But I can do a little bit better than that because I'm given enough information to see that these two sides are the same, which means this is actually an isosceles trapezoid. Whoops, an isosceles trapezoid. Now, what I know about an isosceles trapezoid is like my base angles are the same, but that also means that if I was to draw in this other diagonal here, PR, because the question is asking me for PR. Even though PR wasn't drawn in here, I was being asked for PR here, there's going to be some symmetry in this problem. And so I know that PR is going to be the same length as SQ. So I know that this is going to be 5 centimeters. There's a beautiful little bit of symmetry in this problem. Here, look at the shape here. These two sides are the same. These two sides are the same, but they're smaller than this one. This is a kite. Okay, and now I'm asking you for WX here. Well, one of the things about a kite is that these two sides are the same. Well, so are these two sides. So I know that WX has to be 1.5 centimeters. Okay, that's easy. Let's take a look at another one. So in this case right here, I'm looking for angle L. Now, taking a look at the shape that I've got here, right angle, right angle. Okay, these two sides are the same. So this is a square right here, which means I know that this has to be 3 centimeters. But the overall shape has got to be a right, a right trapezoid. Okay, that's where I recognize this shape from. Now, this whole side here is 5, but because this is a square, this little side here has to be 3, which means this little bit here has to be 2. Whoops, not 20. What was going on with that? 2, okay, 2 centimeters. So from there to there is 2, here to here is 3, and I know that this must be a right angle because I've established that this has got to be a square. Now, to get angle L, this side is opposite, this side is adjacent, so this is going to be the tangent of angle L will equal 3 over 2. So angle L is the inverse tangent of 3 over 2. Let's go to the calculator and let's figure that out. Okay, inverse tangent of 3 divided by 2, and to the nearest degree I get 56 degrees. Okay, and that's what I'm looking for.